Well, first of all, I would like to thank the organizers for inviting me here. I think it's an extremely interesting program and a very interesting conference, so thank you very much. Well, and I'm not really from the field. I'm a soft matter or polymer guy for many, many years, but I was always interested in the topics which you're working on and dealing on here. And the question I would like to address here is to what extent really classical polymer physics concepts might help in understanding certain things or might help to sort out a few things. If I look at Sam Edwards, you probably think pushed back in the times when you were at Exxon and I was a postdoc there, and we discussed many topics along these lines. And the work I'm going to talk about is the work mostly done with Govardhan Reddy and his PhD student, and it started when Govardhan was a Humboldt Fellow in Mainz at our institute. The other work I mentioned here, we can talk about on the side, but I think I'm not going to talk about here. That is about using machine learning methods to analyze conformational fluctuations in IDPs. That would go in a different direction here. Okay, so if I think of a typical soft matter system here, that is the kind of systems we are interested in. So this is a small polymer with water around. So an all-atom model. This is a highly idealist model of a membrane, which goes back to work with Marcus Tesano. Some of you might know him here. This is an adaptive resolution simulation of an elastic network model of a protein with an all-atom description of the active center and the ligand. And this is an IDP, a picture taken from Hitz in Heidelberg. So this is the kind of systems we are interested in, and from my point of view, they are already damn complicated. From your point of view, in most cases, that's highly idealistic and by far too simple to do anything. And of course, this is one of the questions which we are discussing here. Where can we get these aspects together? And when you think of a typical polymer and an IDP, so this is an example of a short polycarbonate chain, which is one of the very few commodity high-tech polymers. So this is polycarbonate. When you have a typical lenses and cameras, it's typically polycarbonate. Car lamps are polycarbonate and things like this. So optical grade material. And this is an IDP. And you know, this looks like they are similar, but this might be, of course, completely wrong. It's just getting you on the wrong track. But maybe there are a few things which one might use from what we learned in the last 50 years about these systems, one might apply in the other case as well. So there are a list of properties or problems for IDPs. I think I don't have to go through all of them, but there are differences and similarities, but of course there are also a number of different aspects. So the work I'm now going to talk about is about very simple simulations of polyglutamine in water and polylysine in water, and then polyglutamine and polylysine with mixed solvents. And it goes back, as I said, to a longer visit of Govardhan Reddy in Mainz at our lab. And he came to me and said, yeah, there are experiments on these chains, and these experiments are kind of contradictory, and they claim these experiments can be used to infer or to get information about liquid-liquid phase separation in biological systems or in test systems, so that one can use these single chain properties to get information about more complex systems. And the question which I would like to answer, or which I would like to ask here, is to what extent can one really do this? And if one wants to do this, what does one have to consider in order to be able to do this properly? So for this, let's first go back to the classical phase diagram of a polymer system. So what you have here is you have a temperature axis, and here you have a concentration, and there you have the inverse chain length. And when you are at the so-called Theta temperature, that's the temperature where the excluded volume interaction of the monomers with respect to each other in the solvent and the attractive interaction coming from the quality of the solvent just cancel each other. So first approximation. It's more complicated in some details, but roughly this picture is correct. So that the polymer chain can be described as a random walk. And when you now go down in temperature, when you have an upward critical solution temperature, eventually you have phase separation into a dilute region of isolated globules and a dense region. And what is important here, this line here goes down with decreasing chain length, n to the -1, and only in the limit of n going to infinity, you really have this sharp transition here. And when you are not at extremely long chains, you have to take into account these finite size effects. Otherwise, this might lead you into a completely wrong direction. And this is one of the points which I'm going to make here. So these are the systems we look at. And in the case of co-solvents, we are looking at simple models with two different co-solvents, urea, which denatures a folded protein structure. Denatured sounds kind of negative. For polymer physicists, it's a good solvent. It makes the solvent into a good solvent because the chain expands. And the TMAO, which just does the opposite. And these are the two systems which we are going to look at. The experiments, the two experiments we specifically compare our results to are FRET and forced fluorescent correlation spectroscopy, but one can also, for instance, take scattering experiments, X-ray, or if one would have neutron scattering, which would be even better, but I don't know of any neutron scattering experiments because it's not so easy to deuterate these kind of chains. And when you read these papers, these results come to different conclusions based in principle on the same system. And the model we are now going to use, and this is not so important, but model one in detail uses here, but I think this is a nice model for these kind of questions that goes back to Dave Tirumalai. And it's an implicit solvents model where each amino acid chain is made up of backbone beads with one side bead, and of course the side beads are the ones which really make the solubility and the interactions of the side beads. They really describe the solubility of these systems in the solvent. Here are the parameters, and I have more parameters. If you're interested, we can go into that later today or maybe tomorrow. And this is the first kind of comparison. So what you have here is, you have on the one hand, you have the experiments that are the open symbols, and you have the simulations that are the full symbols for poly-Q, so hydrophilic polyglutamine in water. And what is not so important is the shift here of the data of green for simulation, green to open to closed. What is important here is that you have here for the end-to-end distance results a curve which essentially says that the chains are not expanding at all. That are really closed globules if you try to get an exponent for the growth of the end-to-end distance out of that. While on the other hand, the hydrodynamic radius nicely increases with chain length. And this is of course something which one would like to understand, and also then understand whether this has any consequence for the behavior of these systems in an experiment. The first hint that one has to do more, so this is what I showed just before, is if one looks at simulation data of the same properties, and of course the advantage of the simulation is that you can calculate all the quantities on the very same system. No? So you don't have to look at different systems. And you see that they are in reasonable agreement here. However, you see also the behavior for very long chains. And if you now take the typical, for the experts here, for instance, when you take the end-to-end distance here for the longest chain, which is somewhere here around 180, and then take the radius of gyration red for the longest chain, which is around 80, that is roughly, the ratio is roughly 6 to 1/2. So that is reasonable for a chain close to the theta regime. So for a random walk, this is exactly 6 for the squared, and for this case, it's the square root of 6, the ratio. And this already tells us that in order to infer the solvent quality, I think one really needs much longer chains. And to understand this, one can go back to the classical block model of polymeric systems. So how is a polymer chain constructed? And this holds also for these amino acid chains, and also for all IDPs, of course, with fluctuations. So you start out with a very few monomers, and there you have the intrinsic stiffness along the backbone of a chain. And this stiffness is essentially roughly independent of temperature and of solvent. And then the chain starts to bend over, and eventually, if you are in the theta regime, this leads to a random walk type of behavior. If you are not exactly in the theta regime, then you have there, in simple terms, kind of random walk-like blobs, and these blobs then are arranged with respect to each other so that they repel each other in the good solvent, and you get an exponent of 3/5 of the end-to-end distance, or in the poor solvent where they are collapsed, so you get an exponent of 1/d or 1/3. And this can be described within a scaling picture, for instance, for the end-to-end distance, that the end-to-end distance is described to 1/2, squared to the 1/2, given by the Theta power law, which is just in between the one here, so n to 1/2, times the crossover scaling function n times tau to 1/phi, and this tau is a normalized distance from the theta point, and phi is the crossover exponent of 2. So it's tau to 1/2, and I will come back to that later. So now let's look at the first example. So this is the example of poly-Q, and you nicely see that the radius of gyration, it's a log-log plot, grows with n, and that's essentially a straight line. And the self-similarity of the similarity on short distances here, I think, already from this kind of picture is fairly obvious, but of course this is not a proof at all. So this is the n equals 16 chain, so this chain here, a typical conformation, and this is a n equals 16 chain out of the very long chain of 512. And up to a few end effects where they can bend over, these conformations are very similar. And this is best seen if one looks at the scattering function. And I again can quote Sam. He yesterday said we grew up scientifically in inverse space. And this is again the same inverse space argument. So you have a structure factor of a chain, and at short distances and large q, you see the stiff regime with a q to the -1, which is this rigid rod regime for short chains, and then it bends over to the self-avoiding walk regime with a q to the -5/3. And you can actually approximate this behavior nicely by the so-called non-reversal random walk. That's a random walk chain where you include extruded volume along the backbone by 1, 3 up to 1, 6 elements. And if you do that and beyond that, allow the system, the monomers to overlap, one typically can describe these systems very well, up to a few extensions. And that means that these chains here, the poly-Q, essentially behaves very rigid or more or less rod-like up to distances of about 15 to 18 nanometers. So when you work with chains in experiment which have an extension of that order, you get the same result independent of solvent. And doesn't tell you anything whether it has anything, whether it is leading to liquid-liquid phase separation or not. Now we can go to the next example, and where we have the first unusual behavior. So you see again, that is the poly-L, that is the poor solvent situation. Again, the similarity is nice here, so one wouldn't expect any surprise. However, what you see there, you start out with this kind of blob behavior with nu equals 1/2, so Rg of n is proportional to n to 1/2. Again, this is a log-log plot. And then it becomes flatter, and it looks like a slope of 1/4, so at nu to the 1/4. And of course, this is impossible. No? R squared proportional to 1/2 less than 1/d, R less than 1/d, simply cannot work because it would lead to diverging density. But there are quite a few papers where you see this number quoted. No? And of course, one would like to understand where this is coming from. One knows this from other systems where you have stiff systems, for instance, with some, when it starts to bend and folds back and then sticks to each other, that leads to typical intermediate effects of an effective exponent, which is unphysical in the asymptotic limit. And if you now look here, the scattering function, look at the scattering function, it shows exactly this kind of behavior. Again, we have a stiff chain regime, which is here a little shorter, about up to 15 nanometers, so a few nanometers less than in the other case. And then you see this kind of folding behavior, and then eventually the globule behavior with the q to the -4. So this is wrong. This is not it's not new. It's the q to the -4 from the more or less solid spherical object. And so if you look at the structure of your systems, one for longer chains and A for longer chains, and B look at the scattering function, one gets a fairly good impression what is going on. And this is something which actually holds for all polymeric systems. No? This is a very simple simulation, but if one looks at more complex systems and longer chains, this kind of analysis helps a lot to understand better what is going on. And how different this behavior, this crossover event to for large chain lengths is when you look at, for instance, this ratio of the end-to-end distance squared divided by the radius of gyration squared, which for a random walk is 6, exactly 6. For the poly-Q case, which is for good solvent, it starts here for short chains and then it overshoots a little bit and eventually it arrives at the self-avoiding walk value, which is 6.3 something for very long chains. But in the case of the poor solvent chain, initially because of the intrinsic stiffness, you see this increase and then it goes down to the collapse chain, which is somewhere around 3 for this value for long chains. Okay, and the referees didn't believe that this has anything to do with phase segregation. And so what you have here is you have a simulation of a multi-chain system in a regime here where the short chains are above this phase separation regime and the longer chains are, and you nicely see this kind of behavior as expected. Now let's look very shortly at this kind of behavior, where we again have this implicit solvent model with poly-Q with TMAO and poly-L either with urea or with TMAO. And it's again this kind of mean field model for the interaction, so one cannot look at study Q non-solvency effects. I just want to mention this here on the side. So when I now look here at the end-to-end distance or radius of gyration as a function, in this case of TMAO concentration, in this case of urea or TMAO concentration, you see a huge amount of different data, and the question is, can one understand this and can one infer anything from that? Well, the situation becomes more interesting if one plots it in a different way, namely with expansion factor, so it's directly, not the ratio, it's directly Rg squared as a function of chain length for different concentrations of TMAO, or here urea and TMAO. What you see again, you see in the case of a good solvent this nice standard behavior, but then around the theta regime, for instance, you see an initial increase and then eventually a leveling off, and then again this initial increase and then it goes down and displaying the poor solvent behavior. And the same is here with urea and TMAO, again, even way below the theta point, so where you really have a situation where the chains would aggregate at high concentration, you still have this increase of the radius of gyration as a function of chain length, which is way beyond the standard collapse chain type of behavior. No? So this is not enough. And when you look at now at the different quantities of the radius of gyration, hydrodynamic radius, or end-to-end distance, you see that this point where this effective exponent, if you infer a local slope, if this effective exponent is 1/2, namely theta, but of course it's also concentration dependent in this added co-solvent, because you look at these different properties, and these different properties have different corrections to scaling. So the question now is, how can one understand this? And then we make a very bold ansatz, namely that we use this scaling as we had it before, and now replace this x, which is this n times tau to 1/phi, the standard scaling around the theta point, by the distance from the co-solvent concentration at the asymptotic theta. This is very bold, that this plays the same role as a temperature, and it was just a check whether this works out. And when one does this, you find that when you take all these data and replot them in this scaled way, you get a very nice scaling function for instance, the radius of gyration divided by n as a function of this c, that is the c here, times n to 1/2, which means in principle you can take this curve and read off which kind of concentration, co-solvent concentration at n values fit to that value. So you get this universal scaling like in the standard polymer behavior with temperature, now with these co-solvents. And in principle, one should be able to apply this to many different systems and make these kind of master plots if one is really interested to have these master plots and wants to use them. There are some deviations for the shortest chains, and that is the chains where this intrinsic stiffness still dominates. So you have to have chains In order to do that, you have to have chains which are significantly longer than this intrinsic stiffness. But then this classical polymer type of argument, with this very bold transition of a transfer of temperature minus critical temperature over critical temperature to concentration minus critical concentration of a co-solvent over the critical concentration, seems to work quite well and seems to allow to describe these systems in a reasonable way. So this is what I wanted to show you, and I hope that I'm almost, yes, I think I'm in time. So we have these kind of systems, and if one would like to use single chain properties to infer any propensity for liquid-liquid phase separation in these systems, one really needs to know what the longer chains are doing. The data for shorter chains, because of these characteristic chemistry-dependent finite size effects, are not sufficient, and even though one finds this, as I said, in the literature. And I think one can use these single chain properties. However, this has to be taken with great care. And with this, I would like to thank you very much for your attention.
My question serves my own purposes, and I admit that. But if you would take the poly L and poly Q and tie them together and make sort of a block copolymer chain and redo this in various solvents, good and poor, might you see something that resembles amphiphilic blobs with a hydrophobic-ish blob and a hydrophilic blob, and try to get the properties of those at interfaces, the tensions at solvent interfaces, etc.?
Yeah, I think you can use the standard block copolymer concept, as you now
Right.
describe it here, for these systems as well. I don't see any reason why not. You only
Right, I think if the way that you did it here is convincing for this audience, whereas if you just wave your hands and say block copolymers, it's not.
Yeah, you're right. But I think, yes, okay. I think you can do this, yes.
Thanks for the talk. Can you help provide some physical intuition for the nu equals 1/4 scaling that you reported? You gave an explanation, but I didn't quite process it.
This nu equals 1 is for short distances, and so you have here a bond, and then you have the next bond here, but because of the chemical constraints, it can only wiggle a little bit around. And then the next one comes, and you need a long bending distance. So this persistence length is essentially something similar like the effective bending distance of a chain.
You're asking about the 1/4.
Yeah.
No, there's 1/4.
Sorry, you explained the persistence length.
But the 1/4 is exactly what you have is, if you are let's say way below the theta point, so that you have a strong attraction between the beads, and then you have a stiff chain, and it starts to bend over, and then it can come back and sticks here. And this leads to intermediate exponents which are below 1/3, which asymptotically are impossible. And 1/4 is a typical exponent one quite frequently sees when one looks at the systems with this kind of behavior.
Kurt, thanks for the talk. I feel funny asking this question with Ben in the room, but I'm going to ask anyway. My memory is that polyproline might have a persistence length of like 10 or 15 nanometers, but most other polypeptides you would expect to be much shorter than that. So I'm kind of curious, this sort of 10 to 15 nanometer range seems quite high for these, to my eye and my memory of the experiments. Do you have any comment on that?
That might well be.
Okay.
I looked at some other IDPs where we did not analyze this in a very systematic way, because you have, in polymer language, a random copolymer type of structure. But this is a quantity which one has to check for every system individually.
More questions? Since we are speculating already, could you speculate how one can extend these ideas to more random or more heterogeneous polymers, like the ADPs we're interested in biology?
If you have a system, let's say, if you make your chain very long, no? And if you at some stage have a periodicity in sequence, which might be very long, but significantly shorter than the overall length, then these kind of arguments should directly work. But you run into trouble when this minimal length of periodicity approaches the chain length. No? Then it gets difficult. Unless you have effective interaction patterns, which are also similar, no? Then of course it can be the same again. No? But rigorously, it has to be like this.
Right, any more questions? If not, then can you maybe speculate a bit on this bold ansatz that you state essentially by replacing temperature with concentration? Like, is there a deeper meaning as to why this seems to work so well?
Naja, this, if you have a characteristic energy, so to speak, for the interaction, and you assume that it is additive for different amounts of co-solvent, this leads to this linear kind of transfer. But if it's not additive, that if there are other local effects of rearrangement, then I don't expect it to be that simple anymore.
Right.
Just one more if there's time.
I think he was first, then I'll.
You mentioned explicitly that the model you used cannot account for non-co-solvency.
Yes.
And can you just speculate on whether you expect the situation to be any different when they're in this situation?
Okay, co-non-solvency is a specific phenomenon which you have when you have a polymer in good solvent and a mixture of two good solvents. The famous example is polynipam in water and alcohol. And there you have a polymer chain in water, and you add a little bit of alcohol, and then the polymers collapse, and then you add more alcohol, and then the polymers expand. And when you have these type of mean field models with an implicit solvent, you cannot capture this effect, because this co-non-solvency effect comes from the following reason. Alcohol is a significantly better solvent than water. And that means if you have a little bit of alcohol, the alcohol is kind of sucked in by the polymers, and the polymers are compacted to have as much contact to the alcohol as possible. You can measure this, that the alcohol concentration in the rest of the solvent goes down. There are NMR experiments which show this. And then when you add more and more alcohol, then you have all the alcohol contacts on the chain, so to speak, saturated. And since alcohol is a good solvent, the chains again expand. And this is, that is called co-non-solvency. But for this, you need the discrete nature of the solvent particles. You cannot, in such an effective intrinsic solvent model, you cannot capture these kind of effects.
I invite the next speaker to already start setting up, and then we'll have one quick last question.
Yeah, very interesting talk. Do you consider, instead of making a correspondence, between temperature and concentration, you make a correspondence between 1/T and concentration? Because from my experience in modeling protein folding, right, the protein folding stability is directly proportional to denaturant, is directly proportional to concentration, like MAO and urea. And if you naively assume the interaction energy is enthalpic, it's also linear in 1/T. So I suspect 1/T would work better than T in terms of correspondence with the concentration. I don't know whether you consider that.
The argument I gave before was with counting the contacts. No? And I think this, I have to think it, but I think this would lead to this direct correspondence of these relative contacts, no? A relative amount of contacts, C minus C theta over C theta and T minus
Yeah,
T
within a
theta
small
over
range.
T theta. No?
Yeah, within a small range.
Yeah,
we look-
I see your point. So
yeah.
I have to think about it and try it out. So, but
Okay.
it's a good point to check.
Okay, thank you.
All right, then let's thank the speaker.